Of a memory allocation. If we've got our low address here and our high address, which with 16-bit addressing is labeled FFFF. I'm not sure exactly who started with this kind of a layout on things, but it's relatively common. The low end of this thing is occupied by operating system routines in general, or things related to the operating system. For example, when you do the halt, you remember the halt is actually equivalent to a trap X25. What does the 25 mean? It means that if you go down into these low numbered memory locations, specifically to memory location 25 hex, there is contained in that memory location the starting address of the routine that's used to shut the system down. Now that routine, as you have seen, when the thing finishes and you end up on your display as to where the program counter is, that routine is actually in the upper parts of the memory. But they always put these so-called trap vectors down here in this part of the memory. There are some other trap routines that we will talk about, located at different memory locations down in there. In the initial development of computer systems, they handled peripheral devices through what were called channels. That is that there were hardware connections that worked on the thing, and that's how you communicated with it. And they often involved very special instructions. That there were particular instructions that you would use for handling input and output, and for different devices hooked onto different channels on the system, the instructions were different. And so it tended to inflate the instruction set on the system, because even if on your computer you didn't have a device connected, the language had to be able to handle all of those channels. And you would have one for the operator's console, you would have one for disk drive and tape drives and you know, whatever else you might have connected to it. You had to have those because at some time in the future you might want to add that device, even if you don't have it right now. So they were always there. Now somebody came up with the great idea of what is called memory mapped I/O. That is, we have these upper regions up here where you store these addresses are linked to devices. And for example, one of them will be the screen on your terminal. And so to print something on the screen, you use the same instruction that you would use to just put something into memory. You say store at such and such a location. The only thing is that location isn't actually in memory. That location is associated with the device. And so now we don't have to have special instructions to handle input and output. We use store and load. Okay, to print something, we just store it at the appropriate memory location. To read something, we load the register from a particular memory location. Now, that concept is simple enough. The problem is, compared to the processor, you are incredibly slow. I don't care how good a typist you are, if you can run 200 words a minute, the computer can still outdo you. And so if you're trying to read a sequence of characters that you're typing in, between the one character and the next, the computer says, "Help, what do I do now?" And if you just have it reading that data buffer, we call it, from the terminal, it's going to read that first character you type about 5,000 times before you type the next character. Okay, we can't have that. So, what we end up with, and here's the way it actually works on the LC3 with the specific addresses that we work with. We have two different registers. The keyboard data register and the keyboard status register. And let's see, the addresses, the status registers are FE00. And this one is a FE02. Here's the way it works. The status register the most significant bit out here, bit 15, tells you what's going on out there at the terminal. Here's the sequence of events. You hit a key, the ASCII code is put in the keyboard data register, and this is all done in one step. Bit 15 of the keyboard status register is set. When we say set, that means it changed to a 1. Now, when you read the keyboard data register, bit 15 of the status register is cleared. You have one shot at reading that thing. As soon as you read it, that clears that bit. Now, that's used, you see, in order to keep the system from overrunning itself. It's probably less significant on reading from the keyboard than it is from printing to the screen, but we'll kind of look at this thing. So here's a sample of the kind of thing that one might use to read in. Well, let's go this route. We're going to read in a string of 4 characters. Okay, so down here, as we start working through this thing, I'm going to have my string, well, let's just I'll block off 4 words down here. Now, see, I need to get to these things, but if I'm working in address 3000 range, I can't get enough offset in 9 bits from the PC to get to these. So I've got to have some memory locations that help me get to them. So we'll say keyboard status register, we'll fill that with FE00 and keyboard data register FE02. Okay, now I'll start setting up here. I'm going to run a loop. I'm going to loop through this thing 4 times, reading a character each time through. So I will, let's see. Better put the hex on that or else convert it. I'm going to use, let's use register 4 as our loop counter. So we'll clear register 4. And then we'll add 4 into it. And then I'll decrement that. It's a lot easier, remember, when we write things in C, why we like to start at 0 and count up to 4. If you do that here, then in order to check the termination of the loop, you have to check to see if your loop counter has gotten up to 4. That's going to involve doing a subtraction where you have to knock the thing and add 1 to get the negative of it, and then add it, and then look at the result. By counting down, all you have to do is when that loop counter hits 0, you're done. You don't have to do any of that other stuff. So it's just easier here at this level to count down than it is to count up. Okay. In order to work with this thing, I'm going to get the address of that. Into, let's say, register 5. I'll load the address of my string into register 5. Now, I think I'm all right here to start my loop. The basic process that I have to go through on this thing is that I have to check my status register to see if there's a character out there ready to be read in. As long as there is not, I'm just going to spin my wheels. Okay, so we do this by doing a load, remember this indirect addressing mode? I'm going to, the indirect says that you go to this location, but that's not your data, that's the address of your data. Okay, so it allows me to jump to here, which is my keyboard status register.
So that's loading the value inside that.
It's loading whatever's in here. Now the only part of this that I really want to look at is this. There are some other things in there, but we don't need to worry about them. All I want to look at is this bit. If it's a 1, remember, that means that some key on the keyboard has been pressed. If it's a 1, that makes this number negative, whatever it is. So as long as it's either 0 or positive, not negative, I'll just keep checking. Okay? Then what we call busy waiting. It's just going to sit there and repeatedly keep checking that register until it sees a 1 in bit 15, which says, old slowpoke out there on the keyboard has just pressed a key. I had a student one time that took an interest in that and said, I wonder how many times it will actually loop between key presses. And he checked it, and it was literally in the thousands. It just loops and loops and loops in there until you finally press a key. Now, when you press a key, it sets this to a 1, which is now going to make that thing appear negative, and so I will not take this branch and I'll go on to the next instruction. Now, what do I want to do on the next instruction? Well, I want to get that character out of the data register, so I will load indirect register 0 from the keyboard. Remember, this label does not actually get associated with that register. It's down here. This is the thing that's associated with that register. That's why I have to have the indirect. The examples in the book, they don't use these labels, they just use A and B. Now, as soon as I do that, as soon as I read it, bit 15 is set back to a 0. Now, there's some significance to that. As long as this bit is 1, it will not accept any more data from the keyboard. If I don't clear that, that keyboard is locked. Nothing's going to be received. As long as that's a 1, nothing's going to happen. As soon as I read it, that clears it, and now it's ready to receive the next key that you press. Now, I've got some other housekeeping I want to do here, but believe me, it'll get done before you press the next key. I want to store that in my string. So I use this store relative where? Well, let's see, register 5 has my address, and I will offset by 0, so that puts me right there. Now I want to set it so that the next character I read goes into the next memory location, so I will increment register 5. Register 5, 1. And want to decrement my loop counter. Register 4 -1, and we'll branch it plus 2 loop. And for our purposes here, we will help. Okay, now let's kind of trace this thing through here and see what happens to it as we go. Let's see, I am using register 0, register 1, register 4, and register 5. Let's see, starting at 2800, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13. This is 280D. Four locations there, D, E, F, 2810. Okay, we begin by getting a 4 into register 4. So there we are. We load the address of string into register 5. Well, that's 280D. This is my string. And now we're set to start the loop. Okay, I wait here until a key gets pressed. For the sake of discussion, let's say that we that our input is ABCD. Okay, the first one gets pushed, the uppercase A. We load from our keyboard data register into register 0. What we get is the ASCII code for A, which in hex is a 4-1. Okay, so we get that into there. That clears the busy bit, we sometimes call it, in the keyboard status register. So now it's ready to accept the next character. And if it should get typed in before I finish all of this, that's okay. It'll just hold it. It'll lock the keyboard, and if somebody presses the C, why, it will just kind of go by the wayside. So now we store that into the location whose address is in register 5 plus the 0 offset. Well, that's 280D. So we get out here and we get the 0041. Now we add 1 onto register 5. We subtract 1 from register 4. That's still positive, so we go back up and we try it again. Now, again, we sit here and spin our wheels for a few thousand cycles. When old Slowpoke out there hits the B, then all of a sudden that status bit changes to a 1. The contents of this thing will now be negative. It will not branch, and we go down to here. That thing going negative says there's new data in the data register. That's really what it says. So we copy that into register 0. Now the ASCII code for a B is 0042. So we get that into register 0. Now we store it in memory at the location whose address is in register 5. 280E. So we go out here and we get 0042. Add 1 to register 5. Subtract 1 from register 3. And if it's positive, we go back up to here. Okay, wait again. The C is hit. We get 0043. It's nice that those ASCII codes for the uppercase letters are nice and sequential. We load it into register 0. We store it at this one, 0043. Add 1 here, 2810. Subtract 1 here. That's still positive, so we branch. We read again, we get the D, which is 0044. Gets loaded into register 0. Copy that to this location. Add 1 here. Decrement 1 here. Now it's no longer plus, it's 0, so it does not branch and it will halt. Okay. That's a basic input routine. Now, let me point out something about this. Suppose instead of A, B, C, D, we had entered 1, 2, 3, 4. We want to enter the number 1,234. The ASCII code for 1 is 31, right? Yes. So what I would get, these things with just 3s in them instead of 4s. But I want the integer value, 1,234, in one memory location. See, when I say in C, if I say scanf the X, and I type 1, 2, 3, 4, in memory location X, I end up with 1,234. Here what I have ended up with is a character string of ASCII codes. Now if I want to get that to 1,234 and store in some memory location X down here, I've still got some work to do. But guess what? What's coming in from your terminal, even when you're working in C or some other language, is a string of ASCII characters. That's what your keyboard generates. Every time you press a key, it's generating not that number, but the ASCII code for that character. That's what's actually being generated. Someplace in there, there's a routine that goes through and takes care of all of that. Okay. We haven't got time to do it. Here's the strategy. I will take this number. Fortunately, all the digits are in there, and it works out pretty nicely. I will subtract 0030 from that number. And that'll just strip off the ASCII coding, and I get a 1, which is the value that I was really after. If that's the last character, I'll quit. If it's not, and I kind of assume that I am entering stuff in base 10, I will multiply that number by 10, strip the ASCII code off of the next one, and add the resulting digit. Okay, see what I'm saying? We'll do this kind of thing. while not done, multiply, we'll call it X for now, by 10, subtract X 30 from the next character, add the digit to X, and then you go back and look through and do it again until you get down to the last character in the string. It's a little more work than you might think, especially when you stop and think, now, wait a minute, how are we going to multiply X by 10? 10 binary is easy, you just add the number to itself. But 10 decimal is a different ballgame. We got a few instructions to put in there to do that. Okay. Any questions about that? The way we'll do it, by the way, if you want to multiply register n by 10, you do the following. Add register n to itself. Let's see, we may want to put that, no, we're okay. This gives us register n equals 2x. This would give us register m is 4x. And then we add it again. Register m is now 8x. And now you can add register n is now 10x. Taking 8 times a number plus 2 times the number, you get it. Well, anyway, that's the basic strategy and how we have to work with it. We will fuss with that next time. Write a more complete thing to input